Hey everybody, I wanted to tell you about the last chapter here, specifically section one. We're going to talk about systems of equations, plural, right there. And that's kind of the big thing on this, that when we are dealing with multiple equations and multiple variables, that is a system of equations. We want to know how to solve it. So here we go. Here's a good example. In the first one, I have x plus 3y equals 8. The second equation with the same two variables is 2x minus y equals 9. We would like to find a solution for that, a solution being a single point that satisfies both equations. Now, if we only had one of these, let's say we had this top one right here, we could solve that for y, and I'll go ahead and do that real quick here. Um, Subtract x from both sides and divide by 3. We've been doing this all semester, so no big deal right there. But that's going to I have two variables, so I can't solve this and get a single number. Instead, what I get is a line that shows me all of the possible solutions for that one equation. Here it's the red line. Um, you can see that my slope would be -1/3. My y-intercept would be 8/3. So they've come up here. Here would be 3/3, 6/3, a couple more would be 8/3 would be my y-intercept right there. And then it's going down. Every time it goes down one, it goes over 3, down 1 over 3. So that red line would be that first equation. And you could do the same thing here with the second one. I got my colors mixed up. I should have done red up there and blue down here. Whatever. I'll do green. How about that? And if I solve this one for y so that we could easily graph it, I'll subtract 2x from both sides. Would look like that. Multiply through by -1. You'd get y equals positive 2x minus 9, like so. And you can see that's the blue line here that you have. If you trace this on down, the y-intercept would be down there at -9, and then it's going up 1, I'm sorry, over 1 up 2, over 1 up 2, and I've got that slope right there. The graphical way of doing this would be what we just did. Graph both points and look and see where they cross. That point right there is the solution to both of these. And this system of equation, also sometimes called simultaneous equations, is has got one point right there where those two lines cross that lies on both lines. It satisfies both things. And if I took x equals 5 and y equals 1, from the point right there, then I could put it in up here and I'd get 5 plus 3 times 1. Up, indeed, that is 8. So it works there. And then down here, I'd have 2 times 5 minus 1. Sure enough, that one's 9. So we found a solution for this system of equations that satisfies both things. We did this with the graphing method or graphical method where we just graphed it and looked to see where they cross. There's a couple other ways that we can do that, and I want to show you those as well. Here is what we call the substitution method. I've got the kind of the game plan down here for you, but when we substitute, we're going to have to solve one of the equations for one of the variable. And it's good if you pick the simplest one, just to save yourself some work. Is there a simpler one here? I don't know, maybe, maybe not. But I could pick either equation, and going with the simplest one kind of usually makes things easier. So let's say we take this top one. I solve that for one variable. Doesn't matter which equation, doesn't matter which variable, but sometimes things are easier, if you kind of scout around and think about it. I'm going to subtract 3y from both sides. It'll cancel on the left. This top equation, when I do that, is going to become x equals 8 minus 3y. Okay? I now know what x is in terms of y. In other words, you tell me what y is, I can tell you what x is. But this little thing right here is handy because I can take this 8 minus 3y and substitute it. Now x is equal to 8 minus 3y. So it's perfectly okay to take that and bring it over into the second equation and substitute it in anywhere that I see x. We're substituting 8 minus 3y for x. We're just replacing x with what we know x is equal to. All right. And once I do that, I can start back up and I can say 2x. But now x is really 8 minus 3y. I've got that minus y in the problem right there. Together, that's all equal to 9. And see how we use that substitution method to knock the number of variables down from 2 to 1. Now I only have one variable, and I can solve an equation with one variable in it. So that's the whole game plan here. We do need to distribute, so 2 times 8 would be 16. 2 times negative 3y would be negative 6y. I've got the negative y there. That's equal to 9. I can combine these, and that'll give me 16 minus 7y equals 9. We'll go through and subtract 16 from both sides to cancel it on the left. And when I do that, I'll have negative 7y equals 9 minus 16 would be negative 7. Clearly, I need to divide by negative 7 here to get y by itself. And you can see here that y is going to be equal to 1. All right. We now have one of the answers. We now know what y is. So we went through, we solved the simplest equation for one variable. We substituted that into the other equation. It's got to go into the other equation. If you don't, you're not using all the information, right? I've got those two lines that cross. If I solve one of the equations, plug it right back into the same equation, then I'm going to get something that either is obvious, like 6 equals 6. And you go, yeah, that's true. Doesn't do me any good, but it's got to go into the other equation right there. So whichever one you didn't pick for the first part. All right, once I've got that number, we can move down here to the third step. Plug the solution, this thing that we just got, back in, and you can plug it into either one, but the easiest place would be right here because this one is already solved for x, right? And so when I want x, all I have to do is say 8 minus 3 times y, but now we just figured out that y is equal to 1. 8 minus 3 times 1, that'd be 8 minus 3 is equal to 5. So we just got the same thing that we did the other way. X equals 5, y equals 1. You could write that as an ordered pair if you wanted to. X, Y, whatever, right there. This is the same problem we just did. We got the same answer. This is the substitution method. Solve one equation for one variable, plug it into the other equation, and then whatever number you get, put that in anywhere. Incidentally, I could have put it into the other equation. I could have taken that y equals 1 and gone right back into here with it. Okay. Um, So that would give me 2 times x minus 1 equals 9. Add 1 to both sides. 2x equals 10. Divide by 2. X equals 5. I could have gone into either equation. I chose the first one in this solved form because it's already solved for x. It just made my life easier, right? But you could do it either way. All right. Lots of options. Just keep the rules and you'll be fine. Here is a second example of this. So substitution method, again, we want to pick one equation, solve it for one variable. Doesn't matter which equation, doesn't matter which variable. If it were me, I would probably take this first equation and solve for y. And you say, why would you do that? And I go, well, because all I have to do is add x. If I come down here to the second equation, I got to deal with these 2's and 5's and stuff. Uh, you know, this real easy. If I solved it for x, I'd have to move y and then get rid of the negative sign. Just do the easy thing, right? whatever looks easiest to you. So when I solve that one for y, I've got to add x to both sides. I'll have y equals x minus 5. That's what I want to substitute into the other equation. So here's this. That's what y is equal to. You can replace y right there with x minus 5. If you had other y's, you'd replace it everywhere you saw a y. It's now x minus 5. All right. Once we have done that, then we get 2 times x minus 5 times y. But oh, y is x minus 5 now. Equals 1. You can already see we're down to one variable. We solve that equation, get a solution, plug it back in somewhere, anywhere you want, and it'll be all right. I'm going to distribute this right here. So I'll get 2x minus 5x plus 25 equals 1. I'm going to combine these like terms. I'm going to subtract 25 from both sides and divide by -3 to get a +8, and then plug that back in. It could go here, it could go here, but the easiest place is right there. So I'm going to go with that one, and all I'd have to do is say y equals 8 minus 5 equals 3. This is a different problem than we did before, but we just got x equals 8 and y equals 3. As an ordered pair, that would be 8, 3. That is the point where both of these lines cross, and that would be the solution to our system of equations. What are these good for, you say? Oh, there's all kind of things in business and in finance and in engineering and in physics where you have different constraints on a problem. You have to have at least this much, and on the other hand, you don't want any more than that. You draw those two lines, they're going to cross somewhere. That's your that's your solution. That's the number that you're looking for. Okay. Um, Now, here is a problem and a new method. This is we could do this with the substitution method. We could do this with the graphing method, but instead we're going to do something called the addition method, also sometimes called elimination method. Okay. And this works really well sometimes. It depends on the numbers and the problems and everything, but it is a third possibility. We could do it graphically. We could do it with substitution. We could do it with addition or elimination method. And essentially, all we're going to do is take the left-hand side of this equation and add it to the left-hand side of this equation. And then we're going to take the right-hand side and add it to the right-hand side. It's almost like we're just taking, drawing a line up underneath this thing and adding straight down. Okay. Why would I want to do that? Because when I take x minus x, that's going to cancel out. If you see a situation where x minus x is going to drop out, remember the whole thing is we're trying to get this down to one variable because I can solve that. But adding straight down to x minus x would give me a 0. So all the x's are gone at that point. 2y plus y would be 3y. Remember, we're adding straight down. -1 plus 3 would be 2. So y is going to be equal to 2/3. I've already got one of my solutions right there. What do I do with it? I plug it back in somewhere, anywhere. I could go in here. I could go in there, whichever one looks easier. Here looks about the same. So let's take the top one, I guess, and we'll go into there. When I do that, I'll get x plus 2y, but I've figured out that y is going to be equal to 2/3. That's equal to -1. We're looking for this x. So if we could simplify this thing down, that's going to be x plus 2 times 2 would be 4/3 equals -1. Clearly, I need to subtract 4/3 from both sides, and that's going to be a little bit interesting. Before we do that, maybe let's write this in um, as a fraction. 3/3 would be 1, so that -1 is going to be -3/3. And now when I subtract 4/3 from both sides, the 4/3 minus 4/3 will cancel, and I'll just have x on the left, which was the whole point of all this. -3 minus 4 would be -7/3 right there. So that would be our x value, the addition method right there. That one got a little bit messy with the fractions. Sometimes that happens. So, substitution might sometimes be a better option. Addition might sometimes be a better option. It's just nice having a bag of tricks and you can pull out whichever one you need. Sometimes one's better, sometimes the other. It's up to you. But watch for that one. In this problem right here, we want to do this one with the addition or the elimination method. And if you look, when I add straight down 3x plus x is going to give me 4x, and 5y minus 2y is going to be 3y, and -11 and 11 is 0. That doesn't really help me at all. Okay. Remember, I was trying to eliminate one of the variables, get it down to an equation that only had a single variable and solve for that variable. So I didn't accomplish that there. So adding straight down is not an option. It's an option. It's perfectly mathematically legitimate, but it doesn't help me. It doesn't move me toward having a solution. It would be okay to subtract the left from the left and the right from the right. I could come through here, draw a line, and instead of adding straight down, I could take the top one minus the bottom one. 3x minus x would be 2x. 5y minus -2x. Minus negative would be adding, so that would be a 9y. Whoops, I didn't get rid of x or y, so that didn't really help me, did it? Um, I'd get this other equation, but it doesn't help. So addition, maybe addition, subtraction, something right there. And you say, why is that even okay to do? Why is it legitimate, mathematically allowed to just add two equations straight down? This one didn't help, so I'm going to erase it here. But the answer is all of this is exactly the same thing as that. That's what the equal sign means, right? It'd be perfectly okay to come along and add 4 to the left-hand side, and as long as I did it here, right? Well, I can add the same thing to both sides, and that equal sign in the middle says that this is equal to that. So if I add this to that and 11 to -11, then I have added the same thing to both sides. That's all we're doing with the elimination method. Um, so let's see what else we could do. I know that I can multiply both sides of an equation by a number. I see that I've got a 3x up here, and if I had a -3x, then 3x and -3x would cancel out. So what we might want to do here is to keep this top one the same. I'm going to rewrite it here to give myself some room. Okay, but I didn't do anything right there. I just copied it over. On this one, I'm going to multiply through by -3 on the left, on the right, distributed everywhere, all that. Okay. So if I take this and I multiply the left-hand side by -3 and the right-hand side by -3, we're still perfectly mathematically legitimate. Distribute on the left, I would get a -3x plus 6y equals -33. And now I have set this thing up where I can add straight down and it will eliminate all of my x's. I could also play little games and eliminate the y's. That would be fine. I just got to get rid of one of the variables. This is probably the easiest way here with the elimination method. 3x minus 3x, those are going to cancel. 5y plus 6y is 11y. -11 minus 33 would be -44, -44. And when I divide by 11, then I'll get a -4. So we've got one answer. I need to substitute that back somewhere, either into the top equation or the bottom equation. You get to pick. I like that bottom equation doesn't have a coefficient of x, so I wouldn't have to deal with the 3, right? That's going to be a little bit easier. So let's drop it in right there. I'll get x minus 2 times y being -4. That's equal to 11. -2 times -4 would be +8, +8. And now I can subtract 8 from both sides, and I've got my x value. There's the solution of this system of equations, two lines that cross somewhere. Actually, now we know they cross at 3, -4. Could have done it with the substitution method, could have done it graphically. You get to decide for each problem what's best, what's easiest, what's the most direct way to do it. Here's another one. This one's kind of a hot mess because there's fractions all over the place. And one way to do this would be to just get rid of all the fractions. Sometimes I call this the fraction bomb. If we just blow up all those fractions, then sometimes that makes it easier. If I could find a least common denominator of 3, 6, 2, and 4 and multiply both equations through by that number, then I'd be rid of all my fractions. I think you can see that that number would have to be 12. So if I multiply the left by 12 and the right by 12, this will turn into, uh, when I distribute right there, I'd have 12x over 3, which would cook down to 4x. And 12y divided by 6, 12 divided by 6 is going to be 2y. And 12 times 3 would be 36. Okay, do the same thing down here. You wouldn't have to multiply by the same number, but here it makes sense. Again, distributing 12x over 2 is going to be 6x. And then right here, I'd have 12y over 4 would be, there's a negative sign involved in there too. That would be a 3y equals 12. Hmm. Okay. Maybe we could have done something else that would have already given us, if we had gone with a 24 up here on top, I would have gotten an 8 here and maybe that wouldn't work. But I might could, find something that would automatically make it happen. All right. So that's perfectly okay too. Sometimes you have to jiggle one or the other of the equations by multiplying both sides by some number. This one didn't really line up nicely for elimination method because there's nothing there that I can do. But I did get rid of the fractions, right? So that's something. Um, Sometimes you just kind of have to try things and see where it takes you. But knowing all your tricks, knowing all the tools that you have at your disposal helps. What could we do here? If I were to turn this into a 6 and that into a -6, that would work. What would I have to do? If I multiplied the top equation by 3, then when I distribute, I'd get a 12x plus a 6y equals, that would be 90 and 18 would be 108. Okay. And then I got to turn this into a -6. So if I came through and multiplied by a 2 on the left and on the right, distributing, I would get a 12x uh, minus 6y equals 24. And now I can draw that line, add straight down 12x, and 12x would be 24x. 6y minus 6y is 0. These would drop out. And I've accomplished what I was trying to do right there. That would be 120, 132, I believe. And then I could divide by 24. Okay. So there's not always a perfect answer for everything. Sometimes you just got to play with it and see where it's going to take you. I should be able to do that, but I'm going to cheat here. 132 divided by 24, 5.5. So you could write that as a fraction or as a decimal. I'm going to go with the decimal here. Okay. And now I've got one of my answers. I got to plug that back in somewhere, and the choice is yours. Lots of choices here. You could obviously, go over here where there's all the fractions and go in here or there. Um, I don't think I would do that. I'd probably pick one of these two or one of these two. And again, it doesn't matter. Um, let's go into this guy right here. So I'll take the 5.5, replace x with that, and let's see what we get real quick here. 6 times 5.5 minus 3y equals 12. This is before I multiplied by 2, that second round. Okay, I'm down to one variable, and I should be able to solve for that. I'd have 33 minus 3y equals 12. Subtract the 33, I'd have negative 3y equals 21, I believe. Divide by negative 3, and I get y equals negative 7. So there's the other one. The point would be 5.5, negative 7. I can hear the math people howling from here that there's a decimal in there. Maybe, maybe not. I don't know. They're funny about that stuff. But that would be the x and the y, the solution that would satisfy both equations. Okay, I wanted to show you a couple weird things that can happen. Let's just look at the graph of this one. X equals 9 minus 2y is the first equation. Second equation, x plus 2y equals 13. I've already graphed those over there for you. Clearly, you'd probably want to you could do a couple things here, and you already know all these tricks, so I'm not going to go into. I could, solve this for y equals mx plus b. Looks like they've already done that right there, and then graph it the regular way. You could make the little table and plug numbers in. Maybe it would make more sense to go yx here because it's x in terms of y, and then get those points. Just remember to flip it back around when you do the thing. You also could come in here and say, well, if I let y equals 0, then I'd get x equals 9. If I let this be 0, all that. You could find the x and the y intercept and just draw that line. All right. Point is that we have graphed these two lines and they run parallel to each other. What point satisfies both of those equations? What point lies on both lines? The short answer is no solution. So this is kind of a weird thing that can happen here. You're not going to get an answer because there is no point that lies on both lines. Okay. If you came through and did this with substitution, I could take this 9 minus 2y, replace x with it, and I get 9 minus 2y plus 2y equals 13, and the 2y's, negative 2y and the 2y would cancel. I get 9 equals 13. Okay, 9 does not equal 13. When you see that, it means there is no solution. I could work with this and do the elimination method. And again, it would just turn into a big mess. There is no solution. So sometimes that happens in real life, and that means you got to move on. You got to change the situation. So those aren't the two equations that we're trying to model. Here's another interesting thing that can happen sometimes. Again, I've already graphed this. X plus 3y equals 2 is going to be that red line going down. And the second equation, 3x plus 9y, is the blue line. They are the same line. Okay, it's not one point that's a solution. If it's a solution of the first equation, it's also a solution of the second equation. Here, technically, you have infinite solutions, infinite number of solutions. I'll put, yeah. And why? Well, because this one's a solution. This one lies on both points. It lies on both lines, right? All of these points are on both lines, so they're all solutions, and you could trace that all the way out to the ends of the world. Okay. Check this out. If I were to take this top equation and multiply both sides by 3. 3 times x would give me the 3x. 3 times 3y is the 9y. And then over here, 3 times 2 is 6. See how the bottom one is essentially the same equation as the top one? These are called dependent equations because the second one depends on the first one. Okay? you're not going to get a solution, a single point solution in that situation. You need independent equations like the other ones we've been looking at. All right, so that's a possibility. These are your choices. You can do it graphically. You can come in here and say, all right, I got my first line that does this, and the second line is going like this. And there is a point, an answer right there. If you can look at a graph, if you can put these in on your calculator and graph them, that's an option too. Remember, there is that functionality of solve an equation. Let me just make up something real quick here. If I came in here and the first equation was y equals negative 3x plus 2, and the second equation was 2x minus 4, and I hit graph, there is a point where those meet right there. And I could find that point using the calc functionality. Second trace gives me calc. I want the intersection where those two lines intersect. And as always, you got to give it a little bit of information, which is the first curve. Pick either one, doesn't matter. And it's going to jump to the other curve. Is this your second curve? You go, yep. And then it says, where do you think? And about there. And it'll go find it that way. Okay. So that's, even another option that I guess I should put up here with with the calculator. Where am I? There you go. So that's an option too. That works real good for two-dimensional problems where you only have two variables, X and Y. If you get off into three-dimensional, 16-dimensional problems, it's not so much fun. Okay. In fact, all of graphical might kind of step out of the room at that point. The substitution method, we solve one equation for one variable, plug that into the other, sub into the other equation, solve that. That's going to give us a solution. Plug that solution into some equation, either one. Okay. All right. Substitution method works really nice, just about always. Even if you had 16 variables, you could do it that way. The elimination method, we're adding or subtracting straight down. The left on the straight down. Okay. Um, we may need to multiply one equation by something else to fix it, to multiply both sides of one or the other of the equations. And we saw some of that. I don't know if you had, 2x minus y equals 4 and x plus 4y equals 8. I see that 2x in this right here. If I had a 2 right there and subtracted, you know, that would be pretty easy to do. So I could multiply by -2. I'd have to do it here too. That'd give me a -8. Multiply by -2 be -16. Then I could add straight down. Make sure one of those cancels out like that. Okay. So that is first go at systems of equations, and they're kind of fun to do. They're kind of nice. Thanks for stopping by. Bring your questions to class, and we will figure it out. Thanks.